We're ready now to talk about types of equilibria. By the way, equilibria is just the plural of equilibrium. Let's recall that the equilibrium point is the intersection of the null lines. In other words, it's a point where both dx1 dt is 0, so no motion in the horizontal x1 direction, and also dx2 dt equals 0. So no motion in the vertical or x2 direction. So it's a point where there's no motion at all. For the types of systems of differential equations that we're covering in this class, the equilibrium point will always be at the origin. Now, the big two categories of equilibria are stable versus unstable. And to explain those, I'm going to use an analogy. Suppose I throw a ball against a wall. So here's my wall, and here's my ball. And I throw the ball against the wall. Now, what's going to happen when the ball hits the wall? Is it going to continue to move forward? No, the wall will stop it. So there will be at least one point in time there where the ball is not moving, and so that is in equilibrium, or an equilibrium point. Now, it's not moving. Does that mean it's not going to go anywhere? It's just going to stay there? No, because the wall exerts a force on the ball and bounces it back to me. Now let's suppose my wall has Velcro on it. So I have a Velcro wall, and let's say I'm throwing a ball made out of Velcro. So I have a Velcro ball. I throw it against the wall, and it can't keep going forward. The wall stops it. Is it going to stay stopped? Well, in this case, yes, because even though the wall still exerts a returning force on the ball, the little hooks and loops on the Velcro exert a force that resists the bouncing force off the wall. So in this case, yeah, my ball just stays there. Again, there's no motion at this point, so it's in equilibrium, or equilibrium point. In this case, though, we would say it's a stable equilibrium because the tendency is for the ball to just stay there. The ball enters a stable state of being stuck to the wall. Versus this equilibrium point that only lasts for a moment and then gives way to motion again, that's an unstable equilibrium. Now, a more mathematical definition of what it means to be stable is an equilibrium point x hat of the system dx dt equals a times x of t. That equilibrium point is stable if every solution x of t, so every x of t curve that's a solution, if every one of those curves approaches that equilibrium point x hat as time goes on and on. And an equilibrium that is not stable is called unstable. Now, what does this mean in terms of the phase plane? For a stable equilibrium, if we trace out all the curves, all curves lead toward the origin, because remember, that's where our equilibrium point always is for our types of systems of differential equations. And when I say they lead toward the origin, notice that means their little arrows lead us, or lead to, the origin. For an unstable equilibrium, at least some of the curves do not lead toward the origin. They have arrows that lead away from the origin.